theorem on a finite dimensional inner product space of a positive dimension. Every self-adjoint operator has a non-zero characteristics vector. Proof: let V be a inner product space of a dimension n where n is greater than 0. Let T be the self-adjoint operator on V. Since V is a finite dimensional inner product space, so it must possess an orthonormal basis. Let beta b equals to alpha 1, alpha 2 and so on alpha n be an orthonormal basis for V. Let A equals to TB, and T is a self-adjoint which implies T equals to T star. We have A equals to A star. Now let W be a space of n into 1 matrices over C, where inner product space xy equals to y star x, then u of x equals to a of x defines a self-adjoint linear operator u on W that the characteristics polynomial determinant x I minus a equals to a polynomial of a is a polynomial of degree n over the complex numbers. Also, every polynomial over C positive degree has a root, thus there is a complex number C such that determinant Ci minus a equals to 0, which implies a minus Ci is a singular, which implies there exists a non-zero x such that Ax equals to Cx. Since operator U is a self-adjoint, it follows from the theorem let V be a linear product space and T is a self-adjoint linear operator on V, then each characteristics value of T is a real, that is C is a real. If V is a real vector space, then we may choose X to have a real entries, then A and A minus Ci have a real entries, and since A minus Ci have a real entries and since A minus Ci is singular, the system A minus Ci into X equals to 0 has non-zero vector alpha in V such that T alpha equals to C alpha.